Good afternoon, everyone. My name is Isuru Ranatunga. I'm a PhD student at UT Arlington. And today I'd like to briefly talk about a project we've been working on. It's called SkinSim. It's a multimodal skin simulation platform using Gazebo. So some of the work we're working on is developing robot skin, so skin for robots that include embedded tactile sensors, accelerometers, as well as infrared sensors. And to do this, we have to worry about a couple of different aspects, such as the measurement simulation models for skin as well as the sensors. And then we have to tell these parameters to the fabrication guys who do MEMS, EHD printing, et cetera. And then finally, we need to worry about the appropriate control and estimation algorithms depending on the types of sensors we developed. And finally, we need to tie all of this down to actual physical human-robot interaction. Because if we develop the sensors and the algorithms and it doesn't work with the people, it's not going to be of much use. So for this, and the main problem is answering certain design questions, such as what sensors do you want, how many of them do you want, and where do you want to place them on the robot? And this is a very coupled problem, and to answer this, we are trying to develop a program called SkinSim that is essentially allows you to place robotic skin on top of existing robots in Gazebo. What that allows you to do is change and play around with the different parameters, sensor types, placements, and then try out experiments with a virtual human, for example. And this will allow you to very quickly figure out what parameters are appropriate, and without actually manufacturing the sensors themselves, you'd be able to optimize your design. So right now, what we've done is started with planar sensors. So we've developed large arrays of planar sensors. We can currently change the resolution of these sensors, the noise models, the sensor models. And what this allows us to do is to actually tell the manufacturing people what type of sensitivity do you want, and how does this affect our force estimation and control algorithms. And as you can see, we do a lot of validation. So every planar sensor or model we use, we validated with real experimental results. This is a pretty tough deal, especially with some constraints we have to deal with Gazebo physics. But we've got some really good results, and you can also see RViz visualization. We have image maps of the tactile data. And we were able to generate very large sensor arrays, as you can see below. And the final idea is to be able to place this on very complex robots, like, for example, a PR2 robot body. And you can see an example, like a prototype example of some of these sensors on the robot. Finally, SkinSim development. We are, of course, going to release this as an open source, and a very early version is going to be available in the near future. The code is going to be available on Bitbucket. The other thing I'd like to talk about is a special interest group. Right now, there's a limited functionality or support for robot skin type devices in ROS. So the idea here is have a special interest group where we can discuss possible standardization as well as support for robot skin. Feel free to join and contact me if you need more information. Thank you.
Hello. Hi, I'm Paul Rosa. I'm in high school. I'm a high school student that loves ROS and making assistive robots. I still have a lot to learn with ROS, but I've been working on building an autonomous wheelchair, and I just recently added an eye control interface for people with ALS. Let me show you the video of this wheelchair. I did my ice bucket challenge with it. Yeah. Cold water, so. I'm going to be releasing that the eye tracking package I wrote pretty soon, and it's just really low-cost hardware for everything. It's just a little webcam and an LED used in remote control clickers, and a hat. So It works both indoors and outdoor. Oh, and duct tape. Um, um, Usually, the wheelchair also runs on, they were using a laptop, but it also runs with a Udaboard, but I didn't want to get my Udaboard wet, so I put a laptop there instead. And, um, so that's the wheelchair I've been working. And I really wanted to learn more about ROS. So if anybody wants a intern, unpaid intern, I'm willing to do that. Thank you. Have a good day.
What is the dongle? There you go. No, this is the wrong one. This is the big one. This one. Yeah. All right, hello everybody. Name is Lorenzo Riano from Bosch. Today I'm going to tell you about Tango, ROS, and the pain in between. So I don't know how many of you are familiar with Google Tango. It's a prototype device that Google has recently released, and it's basically a mobile phone that is capable of tracking its own position and doing 3D perception. So we got one of these devices, and we decided to go on and do some work with it. And the first thing that we did was to do a converter for the log files that converter for the, well, that's a nice video anyway, you can find it on YouTube. It's a converter from the Tango files to ROS bug files. Everything was cool, however, this only works offline. What we wanted to get is an online streaming from Tango to devices. There is already some people who have done it in Java. We want to do it in C++ because we like it, and also because ROS Java still has some problems, and because there is plenty of ROS libraries in C++, PCL, OpenCV, and so on. So this creates a lot of problems, and we went on to solve these problems with the help of Chad Rocky and Julian Celuti. Chad, are you around? Thank you very much. And we managed to get some data going on, and the main problem was that we had to do cross-compiling. But that's not a problem, because cross-compiling is easy. As you can see, this is the only thing that you need to do just to compile a file, because linking is way more interesting. This is probably about 20 static libraries out of 120 plus static libraries, 2 gigabytes worth of data. But anyway, I'm sure you want to see something cool. So how about we do a live demo? Since I am probably a masochist, I'm going to do a live demo doing LinkedIn talk. ROS is running on Mac, and Tango is doing the Wi-Fi hotspot. All right. Where is my monitor? No, stop that thing. Stop the timer. Oh, here you go. All right, I cannot guarantee that it will work. I'm actually pretty sure that we will not work. Yes. All right, so this is Tango, which is tracking its own position. I got 20 seconds to come back. Hold on. Okay, blame it on Google if it doesn't work, but the ROS part definitely does. All right, thank you very much. And in case you're interested, we are hiring full-time and intern positions, so come talk to either me Or Phil, my colleague, is the swimmer-sized guy over there. Bye.
Thank you. Suraj, you're next.
Hi, my name is Suraj, and I work at Qualcomm Technologies Incorporated. So Qualcomm Snapdragon processors have been powering leading smartphones and tablets. They've been designed to be powerful and energy efficient. So I would like to introduce you to IFC 6410, which is a single board computer based on Snapdragon 600 APQ 8064 and processor, which is quad-core and has Adreno GPU in it. So I would like to highlight a few things on this slide here, that this board comes with a Wi-Fi and Bluetooth modules on it, and it currently supports Android KitKat as well as Ubuntu 14.04. So we know that there's huge interest in ARM-based boards because they provide high computation at a very low cost, and there are multiple small-size boards that are available in market today. So IFC 6410 is one of them. But then in the past, we saw that people faced difficulty just to get the Kinect sensor working or the navigation package working on some of these boards. So we took that as a starting point for our project here. And we would like to show you some demos where Snapdragon has enough processing to run computation-intensive algorithms in ROS. All right. Oh. Yeah, I don't know why it's not working. So basically, we have these Turtlebot demos even on the demo room there in our stall, where we have the Turtlebot running the mapping and the navigation package, and all computation is taking place on board, except the RWIS is running on the remote PC. So I would even like to introduce you to FastCV, which is Qualcomm's computer vision library optimized for Snapdragon processors. So I had a demo over here, which was where we had this Turtlebot tracking the red ball using algorithms in FastCV. And what we want to show is there are multiple technologies at Qualcomm which are used in mobile phones, and we believe that these technologies are very useful even in robotics, and FastCV is one of them. So I'd like to quickly talk about Qualcomm and OSRF's partnership that was announced yesterday. So we will now have the Jenkins build farm enabled even for Snapdragon processors, so that ROS users can easily install ROS packages even on Snapdragon-based boards using apt-get. And further down, we'll even have libraries, ROS libraries cross-compiled for Android. Thank you.
Next up is Paul Voss from Ross Industrial.
Hi there, greetings. I'm Paul Vaz. I'm with Southwest Research in San Antonio, Texas. I'm also part of the Ross Industrial team. And today what I'd like to let you know is about two different items. Number one, that Ross Industrial exists. And number two, that immediately following this event, during the Birds of a Feather meeting, we're going to have a Ross Industrial community meeting. It's going to be upstairs. So first of all, this is the website for Ross Industrial. Some people who are unfamiliar with this market may not know, but for, I don't know, the 40 or 50 years of the existence of industrial manipulators, they've basically only been used to do about 3 different things: welding, material handling, and dispensing, like painting. We see a large possibility for doing other tasks, namely things like assembly, blending, deburring, drilling, inspection, and light machining, and furthermore, tapping into a larger market, namely the kind of high mix and low volume market, the kinds of things that heavy industries do and that the aerospace manufacturers do. So we thought that ROS would be an excellent tool to apply to these tasks, namely by creating some universal hardware interfaces, tools, and applications that are targeted toward industrial automation. So who is a part of the ROS industrial community? We've got 2 consortia that have started. One is in North America, and it is spearheaded by Southwest Research, and the other is in Europe, and it's spearheaded by Fraunhofer IPA. If you're curious, in North America, here are some of our members. I think we're up to about 24 members, and we're growing steadily, and thank you all for those who've expressed interest during this event. Fraunhofer has just kicked off in the last, I guess, 2 months or so, so they'll be updating soon with their kind of a list of associates. The second item that I was going to mention is the fact that we are having a community meeting that's upcoming here, I don't know, 10 or 15 minutes from now. It's going to be upstairs, so you got to go up to the 7th floor. It's in the Clark 5 room. There are 4 signs that will lead you to Clark 5 if you're interested. It is open to everyone. It's not just a consortium member meeting, and anyone from the public can come. We do ask that you'd have an interest in using ROS for manufacturing if you're going to attend. And then what is involved is basically 6 10-minute sessions. There'll be 3 that are summaries. So we've got summaries of the 2 consortia, summary of the roadmap that's in a draft form for ROS Industrial, and then we have 3 talks that are all kind of technical, one about Connect version 2, there's one about a Cartesian planner for MoveIt, and the last one is from Mr. Ryan Knighting at John Deere, who's going to talk about a demo cell that he has set up. So that is the gist of it. I also want to give a quick shout out to Sean Edwards, who couldn't make it because he is about to have offspring. So thank you very much, and I hope to see you upstairs. I'll lead one of the groups up there when the Birds of the Feathers join up. Thanks.
Hi, my name is Christian Gebis. I'm from University of Illinois Chicago. I'm one of the students at one of the clubs, EDT Robotics. We basically build all our robots. We have 2 robots, main robots right now. We have one for intelligent ground vehicle competition. It's the one on the left. It's called Scipio. Consists of 2-wheel encoders, a motor controller, GPS, IMU, and camera, and all that data we pretty much use to kind of fuse our ROS system together. The one on the right, it's called Hush Puppy. That's not my name, but so the mechanical named it, and that one is the one for NASA's robotic mining competition. And actually, we are planning on implementing ROS, the stuff that we have gotten to work on Scipio. We're going to plan to have it work on Hush Puppy this upcoming year. So how we excelled in ROS has basically been in, we started last August, and we had no idea what ROS was. We were left with a team that all graduated and did not document their Java robot code. So we kind of had to start from scratch, and over the course of the past year, we kind of got accumulated with ROS and how it works, and basically, you know, some of the failures and improvements that we had was that we did not realize that using absolute position for our robot, it is going to be a drift over a long period of time. So, you know, as many of you know, like Kalman filters and things like that, we actually found this really cool package, Robot Localization, which I highly recommend checking out. It made our air with an area that we traveled about 50 meters. By 50 meters, we came back to a point, and I think it was a 0.1 error. So now, once we started using that, we can pretty much move from GPS point, no problem. We also do, we use one of the ClearPaths Husky, which already comes with ROS. I pretty much put on just a GPS and IMU plug-in into it, and can use that for Scipio, because it's the footprint is pretty much the same for the skid steer system, and that also works with Robot Localization. And Hush Puppy 2.0, this is just the SolidWorks model. We use the SolidWorks URDF exporter, and we exported it as a URDF, but the problem was that it was a four-bar parallel linkage, which is a closed loop, which URDF doesn't support. So we had converted that to SDF format, had to just play around for a really long time to get that closed loop to work. And then now we can pretty much just use the differential drive plugin. So also, I created a ROS meetup in the Chicagoland area. So if anybody likes these types of events, please feel free to go on the meetup site, join us. We had our first meetup already. It was really successful. About 60 members are already part of the meetup community. So I encourage you all to come. Thank you.
Hello, everybody. Let's see, do I just get this to go? Oh, yeah, okay. I'm Buddy Ehrlich, and I just have a personal project that I'm working on that I'm using ROS that I discovered about 2 years ago. And my idea is to build a dog training robot. So that is a robot thing, kind of humanoid, that would be for indoors, for small dogs, would kind of give voice commands and hand commands repetitively, detect when the dog does the behavior, and deliver a treat. And so that's what I said here. And one of the reasons I want to do hand commands, in addition to just voice commands, is my target market is sort of indoor small dogs. My golden customer would be a little old retired lady with a dog in an apartment that wants to train it. So, and some people who are maybe elderly or infirmed, maybe lost their voice, they still do hand commands for the dog. So I'm using both voice and hand commands. One of the big problems, of course, is trying to determine whether or not the dog is doing the behavior. I mean, there's a lot of stuff out there for human poses, and we're really very non-deformable. It's kind of hard to fit into a little space, but a dog and other animals are very deformable, and I haven't had a lot of good luck actually trying to figure that out using my Kinect. So what I'm actually using is a harness that the dog wears with some LEDs that kind of go down its back and that are around it, and that I use these to try to localize where the dog is. Some other things it does are just basic dog training behaviors. As soon as you recognize that the dog does the behavior, use one of these little clicker things, if you ever kind of seen that. So that lets the dog know that he's done the good thing right away, and then you kind of fumble around for the treat, and you look for it and you give it to him. So the robot actually has one of these little mechanical dog clickers, and I use a servo to operate it. I originally tried having a recording of it, but it wasn't loud enough, and I couldn't get speakers that were very good. So that's kind of how I do it. I'm initially going for 5 basic behaviors. Here is one of the first things you teach a dog. It's not come, it's just here. You put your hand down, you say here. The deal is to get the dog to come and put his nose and just touch your hand, or even kind of close up. So I actually use a little touch sensor on the little hand of my kind of robot to detect that. Sit, lie down, stand, and speak, kind of just like a general good category of things to do. I kind of have a pre-prototype that I'm using on a Turtlebot 2, which I think is a great little platform. The low cost of entry was terrific, but I'm definitely having some problems with it. One of the problems I'm having is on my not so shaggy rug, the Turtlebot doesn't work too good. I think one of the front rollers or something kind of hooks up into the strands of the rug. And I'll just show you a little bit where I'm playing him on a torso on top of the Turtlebot, where it actually has a little arm that's going to have the little dispenser inside it to deliver the treats. And that's my thing. Thank you very much.
Hello, my name is Leif Gentoft, and we've been really blown away by what the whole ROS community has been doing lately to make it so that you can get up to speed and start doing research and developing projects more effectively and more quickly. You don't need to develop your own systems anymore. You can pull code from what other people can do. But on the hardware side of things, there's been a decent lack on the grasping side of stuff. There've been some latent developments on both the design of passive mechanics and tactile sensing that it's been pretty hard to get a hold of. And so we're with a team called Right Hand Robotics, releasing a robot hand that's also designed to make it easier to do research. Integrated inside of this, we have tactile sensing, so you can see it's moving till it stops, till it touches me. And we also have passive mechanics, so the hand will shape itself to the shape of the object. We've got about 10 of these in beta at different universities over the world. First of those are shipping out this week at ROS. And the goal of this is to try and give this into the hands of researchers so that you can spend more time on the interesting parts of things. What do you do with the tactile sensing? How do you design a better grasping system, rather than trying to develop the systems themselves? For those of you that were at ROSCON in Hong Kong, since we spoke then, we now have an integrated board on hand that lets you do all the ROS interface over Ethernet and UDP packets. And we've got the full production version of the hand, or the full beta version of the hand all debugged. Also provide some visualizer tools. You can read more on our website. Another thing we're also doing is on the tactile sensing side of things. If you want to install tactile sensors on your systems and interface those easily, we provide a tactile sensing board here you can see on the top that gives you gram level sensitivity. You can chop it to shape, solder it all together, put it where you want it to, and this lets you get up to speed more easily on how do you, on getting good feedback onto your robots. Also, on all this stuff, we're trying to push the price of this stuff down so it's more accessible. For the hand, the one with sensing is comparable to most of the mid-complexity hands on the market right now. We also sell the low-cost version of it without the sensing for $5,000. So we'll be on Baxter on Monday at IROS for those of you that are staying around. Come by our booth or grab me afterwards. We've got this on live demo, and love to answer any questions you might have. Thank you.
Hello. I'm Ashley Napier from Createch. We're a relatively small research and development company, and we sort of see ourselves as a bridge between university-level research and industrial applications. We're involved in a lot of different projects, but one of our main focuses is high-definition radiation surveying. So this is our Envisage probe. We see it as a one-stop shop for assessing the state of your nuclear facility. We've had these probes deployed in various nuclear reactors around Europe, and we've currently got one at Fukushima, which is basically determining what's gone wrong, where the radiation is, and where isn't safe for people to go in and start cleaning up. So it's just trying to make life a bit easier for those guys. This is an example output. It doesn't show up very well there, but we have a 3D LiDAR point cloud produced by this machine with RGB values. But the important thing for us is the radiation overlay, and you can see the brighter spots are areas where you've got higher levels of radiation. So what are we doing with ROS? We aim to make this platform mobile. So currently this is just a big probe that every time we deploy it, it's a custom system. We want to standardize that and mount it on either a UAV or a ground vehicle and just make it more simple for the end user to go and assess the state of their nuclear facility. We've been experimenting with multiple platforms, but we've got a particular interest in UAVs because, for example, at Fukushima, they could potentially go in, fly over the debris, and not get blocked as a tracked robot or something would. This is one of our platforms we've been experimenting with. It's made by Blue Bear Research. They're another research and development company in the UK, and it's a custom platform with a vast sense payload. This is some of our preliminary results from the UAV mapping system. So we've got the RGB D point cloud there. It doesn't really show up that well on this slide. And the important bit for us is that radiation overlay to the left. How is ROS helping us? Well, it's allowed us to do incredibly rapid prototype development. So we can go from idea in a meeting to a system that works way quicker than ever thought possible. Something that we're particularly fond of is the de-risking. So if a company like ours, it's a small company, we can't afford to go off on rabbit holes and tangents based on a good idea. It has to have something behind it. So ROS actually allows us to really have a play with existing things in the community, some things that are similar to maybe what we're trying to do, and really reduce the risk of taking an approach that's not going to work. The modularity of ROS is incredible, and the amount of code that you can reuse. No more boilerplate code. That's fantastic for us. And again, it's extremely flexible in terms of computing. So with the UAV, for example, doesn't have much computing on board, so we can offload that data onto a ground station, do the mapping on the ground station, and that's completely transparent with ROS. It's fantastic. Okay.
Chris, are you here?
Hi, everyone. I'm Chris Swetnam of the University of Hong Kong. If you're at Roscong, you might remember me talking about how we use SMASH for the high-level task planning with our Atlas robot for the Doppler Robotics Challenge. And since then, we were looking for an alternative to SMASH or to the state machines, and that's behavior trees. Now, there's a lot of interest in this. There was a birds of a feather meeting at Roscong. And I've developed a library called SMASH BT that implements behavior trees within the SMASH framework. So if you're not familiar with behavior trees, they're kind of the structured programming equivalent to state machines GoTo. And here you have an example from ROS by Example Volume 2, which is a patrolling robot. And on the right, you have the example implemented with hierarchical state machines. On the left, it's implemented with a behavior tree. Now, all of the failure states are implicit in the structure here, and you have nodes that will do things like run tasks in sequence or select one of a number of tasks. The only possible outcomes are success, failure, or running. And the original formulation of behavior trees come from the games industry, and the behavior tree runs at a fixed rate, for example, 30 hertz, and the entire tree is reevaluated each time. I reformulated this into an asynchronous callback-driven model, and that allows us to do something that the other existing implementations don't do, which is explicitly tell a task when it's been preempted because the higher priority task has been run, for example, or because the condition has been met. So existing implementations, ALMC behavior trees, PyRobot PyTrees, and the Cogniteam decision making, none of them integrate directly with SMASH. The first two don't explicitly signal preemption. The Cogniteam decision making is in C++. I haven't really looked at it, but it is a bit more effort to set up than the Python-based one. SMASH BT is based on Python. As mentioned, integrates quite nicely with SMASH. It works directly with the SMASH viewer. The code will be up at that URL later today. And it lets you wrap up SMASH states as tasks in a behavior tree, wrap up behavior trees as SMASH states, works with the viewer, and it works with the user data and the remapping. That's it. If you're interested, come talk to me. Thank you.
Cameron, are you here? No. Okay. We'll move on to Raffle.
Hello. I hadn't really expected that I could speak, but apparently the one before me wasn't here. So I created a Wi-Fi fingerprinting driving for ROS. I'm just going to show what Wi-Fi fingerprinting is, what I mean with that. What you're seeing here is a visualization of fingerprints, and each column is a fingerprint, a Wi-Fi fingerprint. I'm just going to explain that without this running, because it's, yeah. Okay, there. A Wi-Fi fingerprint is a collection of the visible access points. When you do a scan with your cell phone, you see all these access points, and then you've got the received signal strength. The received signal strength here is indicated by color, and the access point is the location in the stack. So that's all fingerprints at different locations. You can see that they change by location, and this allows us to do localization, but also to do SLAM. Localization is what's done in my promoter's research. So he's been one of the many projects who doing localization inside rooms using Wi-Fi, and I did that. I copied that inside of a SLAM system so that you can enter a building, start walking around, and collect fingerprints. And then later on, you should be able to get back to where you came from using a map created with Wi-Fi fingerprints. So that's like SLAM, but then in the Wi-Fi language. I don't know if that's extremely clear, but I've got this RAD SLAM demo. So the SLAM system I'm using is biologically inspired. on rats. So that you see the boson network in the right upper corner. That's a representation of a rat's hippocampus. I didn't create that. That's Australian research. They do it based on camera images you see in the right lower corner. This is, by the way, sped up by at least 10 times. But this demonstration shows the really Wi-Fi fingerprints being used to create that map of a circular building. It is able to take into account turning, which is rather difficult in Wi-Fi since changing of position isn't really easily determinable, something like that. So I've got this Wi-Fi fingerprinting driver up for ROS, but I don't really have it yet into the wiki, etc. But I would like to give it available to everyone. Thank you for your time.
Hi, my name is Dewey. I'm from a small startup called Robot Base. We are a group of engineers based in New York and Vietnam. We spent a lot of time in the past 12 months working in the Internet of Things space, building AI and machine learning around connected devices. And recently, we got into ROS and really like it. We think that we put machine learning, Internet of Things, and maybe robotics together. Maybe we have something really cool. So what we're building is, and this is the prototype we're working on. It's a 4 foot tall, maybe a little bit taller humanoid that's capable of a few things. Since we're running out of time, I'm just gonna highlight a few things that we're working on that I think may be interest to the group here. So the first thing is speech. So if you work in ROS, you can use the Pocket Swing wrapper by, I think, by Mike Ferguson. But that's to take speech and turn to text. What we focus on is natural language understanding. So after you take the speech to text, how do you understand what that means? How do you understand what the user really wants? And how do you have a conversation with a robot? So we spend a lot of time building that layer of natural language understanding so you can actually send command to the robot, have a conversation with the robot about for some simple tasks for now. Hopefully, when we have some time, we can release it to the group as a package. A couple other things like one feature that we like a lot is connectivity. So we build in a ton of sensor into the robot, and one of I really like a Z-Wave. So with Z-Wave, it allows the robot to connect with the other device at home, right? So it connects to door, to lock, to thermostat through Z-Wave and Zigbee. One of the package that we like a lot is the portable Z-Wave. So if some of you who may be familiar with the Z-Wave protocol, most will be at a fixed. Most will be as a fixed hub at home. It sits in one place in a corner of the house. But when you look at the mobile robot, it's moving around the house, right? So we rewrite the whole packet at the portable Z-Wave that allows us to move room to room and connect to multiple devices. And when we have time, we're going to try to release that to the group soon. Here are the current integration that we have so far. So we work with devices like Nest. So you can send command to Nest to the robot like, hey, can you set the temperature to 65 degrees? That's the basic command. And over time, our AI is going to learn your preferences and your habits and combine with the other sensor to tune those things. And we track things from health to food ordering. So we work with API like food ordering, so you can order food from the robot directly. It remembers your preferences, if you like pepperoni pizza or just a plain cheese pizza and things like that. All right, this is my email. If you like what we're working on, drop me an email. I'd love to talk to you guys more. Thank you.